US Physics Olympiad, year 2020, USAPHO, final round. This year, all competition was divided by two parts. Part A consists of 3 problems, and Part B consists of 3 problems. For each part, it was given 90 minutes. If you want to get more interesting problems, just subscribe for this channel. Problem A1. Breaking up. An infinitely long wire with a linear charge density negative lambda lies along the z-axis. An infinitely long insulating cylindrical shell of radius a is concentric with the wire and can rotate freely about the z-axis. The shell has a moment of inertia per unit length I. Charge is uniformly distributed on the shell with the surface charge density lambda over 2 pi a. The system is immersed in a magnetic field B0 in direction z and is at rest. Starting at t equals 0, the external magnetic field is slowly reduced to 0 over a time t much greater than a over c, where c is the speed of light. Question A. Find an expression of the final angular velocity omega of the cylinder in terms of the symbols given and the other constants. Question B. You may be surprised that the expression you find above is not 0. However, the electric and the magnetic fields can have angular momentum. Analogous to the regular angular momentum definition, the EM field angular momentum per unit volume at a displacement r from the axis of rotation is cross product of r and p as a function of r. P is a vector analogous to momentum given by P equal alpha multiplied by cross product electric field by magnetic field, where alpha is some proportionality constant. Find an expression for alpha in terms of given variables and fundamental constants. Solution for problem A1. Question A. Find an expression of the final angular velocity omega of the cylinder in terms of the symbols given and the other constants. Solution. First, we can use Faraday's law to find what is electric field induced inside cylinder due to change of magnetic field or magnetic flux. It states that integral around circle with radius a will give us change of flux through this circle with a negative sign. That will be 2 pi a multiplied by electric field on distance a equal negative pi a square multiplied by delta b over delta t, or electric field equal negative a over 2 multiplied by delta b over delta t. Next, we can count what is total torque from electric field to the unit of cylinder. That will be total charge, which is 2 pi a multiplied by lambda over 2 pi a multiplied by electric field and multiplied by distance from the center of this cylinder, which is a. And that's equal to moment of inertia multiplied by angular acceleration, which is delta omega over delta t. And now we can put this induced electric field in this equation and find what is equation. We have exact proportionality, that the change of omega proportional to change of magnetic field with the negative sign, and this is a coefficient of proportionality. And now we can just integrate both parts and put limits. Initial omega is 0. It means that formula will be omega as a function of time equal this expression, and finally, because final magnetic field is not 0, but it will be produced by appearing current from a rotating cylinder, and we can count what is this final B. Due to Ampere law, we can count what is integral through any loop like this. Magnetic field multiplied by delta L, and that's equal to mu 0 multiplied by total current through this loop. And here we can use the same technique as for counting what is a magnetic field inside solenoid. If we take a loop like straight line outside cylinder and straight line inside cylinder near the surface of the cylinder, outside magnetic field is 0, and here we just have due to symmetry magnetic field is a constant, and we have total current equal lambda over 2 pi a multiplied by omega and multiplied by radius a. Using this formula we can find that magnetic field proportional to omega and equal to mu 0 lambda over 2 pi omega. And now we can put this expression for magnetic field in our previous formula and find what is final omega for time when total external magnetic field becomes 0. So that will be omega equal this expression, and after that we can take omega out of scope, and finally omega equal this expression. This was solution for question A. Solution for question B. In our case, electric field created by a central wire is negative lambda over 2 pi epsilon 0 r multiplied by unit vector from this direction from wire, and the magnetic field is just B as a function of t in the direction of z. Now let's count what is vector p. That will be this cross product, or alpha multiplied by lambda b over 2 pi epsilon 0 r and multiplied by unit vector in the direction perpendicular to r and z, which is theta. And finally, angular momentum per unit volume is this expression, which is a negative alpha lambda bt over 2 pi epsilon 0 in z direction. Angular momentum per unit length we can just count multiplying this vector by cross-sectional area, which is pi a square. That will be this expression. And now let's find out what happened question A. In question A we had delta omega over delta t equal this expression, and from here we can count what is a change of mechanical angular momentum per unit length. That will be I delta omega equal negative lambda a square over 2 multiplied by delta b, change of magnetic field. If we compare it to previous expression for electromagnetic field, we see that as much momentum we're losing magnetic field, as much we're getting in mechanical angular momentum. And this is true when coefficient alpha equal epsilon 0. So that was a solution for question B. US Physics Olympiad, year 2020, USAPHO, final round. Problem A2. Swoosh. In 1851, Leon Foucault built a pendulum 67 meters tall with a 28 kilogram weight. He connected it to the top of the Pantheon in Paris with a bearing that enabled it to freely change its plane of oscillation. Because of the Earth's rotation, the plane of oscillation smoothly moved over time. If we imagine a large horizontal clock under the pendulum, if initially the oscillation went from 12 to 6, later on they would move to the 3-9 plane, for example, as shown in the figure below. Perhaps surprisingly, the time it took the oscillation to go back to the original plane is longer than 12 hours. In this problem we will investigate why this is the case and what the shape the pendulum traces out. Figure 1. Left. A schematic of Foucault's pendulum. Right. The pendulum motion projected on a horizontal plane in the rotating lap frame. First, consider the case of a Foucault pendulum installed precisely at the North Pole with the length L. We denote square root from G over L equal omega. The angular velocity of the Earth is capital Omega. John is an observer looking at the pendulum from a fixed point in space. At t equals 0, he sees the pendulum at position A0 and with the velocity 0v in the xy horizontal plane. Question A. For John, what are the approximate equations that describe the motion of the pendulum in the xy plane? You may assume that the amplitude of the oscillations is small. We define the coordinates of the pendulum at rest as 0, 0. Question B. What will the coordinates x, y in John's frame be at a later time t? Question C. Ella, an observer, resides at the North Pole, is also looking at the pendulum. What are the coordinates x tilde and y tilde as observed by Ella? Assume that at time t equals 0, the coordinate system of John's and Ella's overlap. Question D. What is the speed of the pendulum bob observed by Ella at t equals 0? Question E. Find the initial coordinates for A, V such that as measured in Ella's frame. Case 1. The pendulum passes precisely through its resting position. Case 2. It has a spike at the points of maximal amplitude, see figure below, instead of a rounded trajectory. Figure 2. Two possible trajectories with a spike left and more rounded right. In a rotating frame, a fictitious force known as the Coriolis force acts on the particles. For Foucault's pendulum, the Coriolis force acts primarily in the horizontal plane in a direction perpendicular to the velocity of the mass in the Earth's frame with magnitude F equal 2m big omega v sine theta, where m and v are the pendulum's mass and its velocity, and the theta the latitude, 90 degrees for the North Pole. Note that when the velocity changes sign, so does the Coriolis force. Question F. How long would it take for the plane of oscillation of Foucault's pendulum to return to its initial value in Paris, which has a latitude of about 49 degrees? Solution for problem A2. Question A. For John, what are the approximate equations describing the motion of the pendulum in the xy plane? You may assume that the amplitude of the oscillations is small. We define the coordinates of the pendulum at rest as 0, 0. Solution. Because John's reference frame is inertial and the point of attachment is stationary, this is a free-moving pendulum obeying simple harmonic motion in each axis. It means that our equations are ax plus omega square x equals 0 and ay plus omega square y equals 0. That was answer for question A. Question B. What will the coordinates x and y in John's frame be at a later time t? Solution. Because coordinate system of John is inertial frame of reference, in common case, solution for the system which is in question A will be r equal a cosine omega t and v equal negative a omega sine omega t. If we use initial position and velocity like this, in that case solution will be x equal a cosine omega t and y equal v over omega sine omega t. So that's the solution, and this is the answer for question B. Question C. Ella, an observer, resides at the North Pole, is also looking at the pendulum. What are the coordinates x tilde and y tilde as observed by Ella? Assume that at time t equals 0, the coordinate system of John's and Ella's overlap. Solution for question C. In previous question we found that coordinates in our inertial frame of reference we had x equal a cosine omega t and y equal v over omega sine omega t. In frame of reference which rotated by angle big omega t, we had coordinate transverse in rotated frame of reference. If we put x and y in frame of reference L, we have x tilde equal this expression and y tilde this expression. This is the answer for question C, and that was solution for this question. Question D. What is the speed of the pendulum bob observed by L at time t equal 0? Solution. In previous question C, we found that coordinates x tilde and y tilde in L's frame of reference are like this. So to find what are equations for velocities, we have to take first derivative by time from these formulas. After that put time t equals 0 to these formulas. So finally we have vx tilde equals 0 and vy tilde equal v minus big omega multiplied by a. So that's the solution and answer for question D. Question E. Find the initial conditions for AV such that as measured in L's frame, the pendulum passes precisely through its resting position. Solution for question 1. If we take equations for L's coordinates, we have these two equations. So first we need to take a first derivative from both of them and look what are conditions for simultaneous Vx and Vy equal 0. That happen only if V equal 0. In other cases it's not possible. So that's a solution for part 1. Question 2. It has a spike at the points of maximal amplitude, see the figure below, instead of rounded trajectory. Solution. To have a spike, we need the velocity to vanish at the extremal points in LS frame. This gives the condition V equal big omega A. Note that in the LS frame this implies releasing the pendulum from rest at some amplitude. So that's the answer for question E, part 2. In a rotating frame, a fictitious force known as the Coriolis force acts on the particles. For Foucault's pendulum, the Coriolis force acts primarily in the horizontal plane, in a direction perpendicular to the velocity of the mass in the Earth's frame, with the magnitude F equal 2m big omega V multiplied by sine theta, where m and v are the pendulum's mass and its velocity, and theta the latitude, 90 degrees for the North Pole. Note that when the velocity changes sign, so does the Coriolis force. Question F. How long would it take for the plane of oscillation of Foucault's pendulum to return to its initial value in Paris, which has a latitude of about 49 degrees? Solution. Since the expression for the Coriolis force only depends on the combination omega sine theta, and since the solution at the North Pole must be pi over omega equal 12 hours, the time at the general latitude must be omega sine theta. And for Paris we have pi over omega sine 40 degrees, which is about 16 hours. That was a solution for question F, and that was a solution for all problem A2. US Physics Olympiad, year 2020, USAPHO, first round. Problem A3. Spin cycle. Cosmonaut Clara is preparing for the intergalactic 5000 race. She practices for her race on her handy race track of radius r, carrying a stopwatch with her. Her race car maintains a constant speed v during her practices. For this problem you can assume that v greater than 0.1 c, where c is the speed of light. Question A. How much time elapses on Clara's stopwatch with each revolution? Clara decides to do a fun experiment during her training. She places two stationary clocks down, clock A at the center of the racetrack, i.e. the origin, and the clock B at a point on the racetrack, denoted as R0. She then begins her training. For parts B through D, we define Clara's inertial reference frame, CIRF, as an internal reference frame in which Clara is momentarily at rest, and which has the same origin of coordinates as the lap frame. Thus, CIRF is a new inertial frame each moment. The times on the clocks and the stopwatch are all calibrated such that they all read 0 in CIRF when she passes by clock B for the first time. Question B. In the lap frame, the reference frame of the clocks, which are at rest, what is the offset between clock A and the clock B? Question C. If Clara's stopwatch measures an elapsed time tau, what does clock A measure in CIRF? Question D. If Clara's stopwatch measures an elapsed time tau, What does clock B measures in CIRF? Solution for problem A3. Question A. How much time elapses on Clara's stopwatch with each revolution? Solution. From time dilation, her clock ticks slower by factor gamma. Therefore, each revolution takes pi r over gamma v, which is this expression, 2 pi r multiplied by square root from 1 minus v square over c square and everything over v. That's the answer for question A. Question B. In the lab frame, the reference frame of the clocks which are at rest, what is the offset between clock A and clock B? Solution. Clara's motion is perpendicular to the displacement between clock A and clock B when they are synchronized in CIRF. Therefore, the simultaneous synchronization in CIRF is also simultaneous in the lab frame. Thus, the offset is 0. To understand why this offset is 0, you can also imagine placing light bulb halfway between the two clocks and having it send a light pulse at some known time. In both Clara's frame and the lab frame, the light pulse reached the two clocks simultaneously. That was solution for question B. Question C. If Clara's stopwatch measures an elapsed time tau, what does clock A measure in CIRF? By symmetry, the speed at which the center clock ticks according to CIRF cannot change. In one revolution, Clara's stopwatch measures this time tau, while the center clock measures 2 pi r over v. So it means then center clock measures tau over square root from 1 minus v square over c square. That's the solution for question C. Question D. If Clara's stopwatch measures an elapsed time tau, what does clock B measure in CIRF? Solution. The readings on clock B and on clock A are not necessarily identical once Clara moves through the circle, because her motion becomes more parallel with the displacement between the two clocks, and thus simultaneity is lost. Suppose Clara is at coordinates r cosine theta, r sine theta, so her velocity is given by negative v sine theta, v cosine theta. Suppose we place a light bulb between the two clocks and having it propagate a light pulse. In the lab frame, the light pulse reached the two clocks simultaneously. In CIRF, the math is a little more complicated. We first rotate our lab coordinates so that A equal negative sine theta x plus cosine theta y and B equal cosine theta x plus sine theta y. We now give the coordinates of the clocks and bulb in the rotated lab frame like this. Clock A is 0, 0, clock B is negative r sine theta, r cosine theta, and bulb negative r sine theta, r cosine theta over 2. In the lab frame, a light pulse is emitted at t equal 0, A equal negative r over 2 sine theta, and B equal r over 2 cosine theta. The light pulse reached the clock A at t equal r over 2 divided by c, A equal 0, and B equal 0, and clock B at t equal r over 2 divided by c, A equal negative r sine theta and B equal r cosine theta. Under Lorentz transformation from the lab frame to CIRF, we have that the light pulse reach clock A at t prime equal gamma r over 2 divided by c, clock B at t prime equal gamma r over 2 divided by c plus gamma v r divided by c square sine theta. Thus, clock B reached the same time as clock A with the offset gamma Vr over c square sine theta in the reference frame, moving at Va equal V and Vb equal 0. Note that clock A ticks slower by a factor of gamma in this frame. Therefore, the time of clock B is Vr over c square sine theta behind the time on clock A. Then we have Tb tau equal Tba tau minus Vr over c square sine theta, or this expression. This is the answer we expect from the rear clock ahead effect. Finally, we use that theta equal omega tau and omega equal 2 pi over t, where t is the period in Clara's frame. Finally, Tb tau equal this expression, and that was answer for question D. And here we finished discussion for problem A3. US Physics Olympiad, year 2020, USAPHO, final round. Problem B1. String cheese. Question A. When a faucet is turned on, a stream of water flows down with the initial speed v0 at the spout. For this problem we define y to be the vertical coordinate with its positive direction pointing up. Assuming the water speed is only affected by gravity as the water falls, find the speed of water v as a function of y at the height y. Define the zero of y such that the equation for v square has only one term, and find y, the height of the spout. Question B. Assume that the stream of water falls from the faucet is cylindrically symmetric about a vertical axis through the center of the stream. Also assume that the volume of water per unit time exiting the spout is constant, and that the shape of the stream of water is constant over time. In this case, the radius r of the stream of water is a function of vertical position y. Let the radius at the faucet be r0. Using your result from part A, find ry. If ry is not constant, it implies that the water has some radial velocity during its fall. In contradiction to our assumptions in part A that the motion is purely vertical, you may assume throughout the problem that only such radial velocity is negligibly small. Question C. The water-air interface has some surface tension sigma. The effect of surface tension is to change the pressure in the stream according to the Young-Laplace equation. Delta P equals sigma multiplied by 1 over small r plus 1 over big R, where delta P is the difference in pressure between the stream and the atmosphere, and the big R is the radius of curvature of the vertical profile of the stream visualized below. R less than 0 for the stream of water. The radius of curvature would be positive only if the stream profile curved inwards. For this part of the problem, we assume that absolute value big R much greater than absolute value small r, so that the curvature of the vertical profile of the stream can be ignored. Also assume that water is incompressible. Accounting for the pressure in the stream, find the new equation relating for Ry in terms of sigma, R0, V0 and ρ, the density of water. You do not need to solve the equation for small r. Question D. After falling for some distance, the water stream usually breaks into smaller droplets. This occurs because small random perturbations to the shape of the stream grow over time, eventually breaking the stream into a part. For the rest of this problem, we ignore the change in the radius of the stream due to changing speed of the water, as considered earlier. Instead, we examine small random variations in the radius of the stream. Random variations can be broken down into a sum of sinusoidal variations in stream radius, each with a different wave number k. We can analyze these different sinusoidal variations independently. Consider a stream of water whose radius obeys Ry equal R0 plus A cosine ky, where A much less than R0 is the perturbation amplitude. To analyze such a stream, it is sufficient to consider only the thickest and the thinnest parts of the stream. According for both sources of curvature, find a condition for R0 and K such that the size of perturbations increases with the time. Solution for problem B1. Question A. We can use energy conservation to answer this question. For a bit of water with mass m, the total energy E is the sum of the kinetic and the gravitational potential energy. E equal 1/2 mv square plus mgy. With this sign convention, g approximately equal 10 meters per second square is positive. As y decreases, so does the potential energy. As the bit of water falls, its energy remains constant and is equal to the initial value. So E equal 1/2 mv0 square plus mgy0. Let's equate them. We have this equation, and solving for v, we have v equal square root from v0 square plus 2g multiplied by y0 minus y. The equation for v square has 3 terms, but we are asked to choose the 0 of y such that there is only one. Evidently, 2 of the terms must cancel, and this must be the 2 constant terms, since the final term varies with y. That means that we need v0 square plus 2gy0 equal 0. Solving for y0, the vertical position of the spot is y0 equal negative v0 square over 2g. With this choice of the 0 of y, the equation for v simplifies to v equal square root from negative 2gy. We know that the result of this equation is real because y less than 0 at the spot and decreases as the water falls. So this equation shows that v is real and increases as the water falls. That was a solution for question A. Solution for question B. The same volume of water must fall through any horizontal cross-section of the stream each second, because water doesn't disappear during its fall and its density is constant. That volume per unit time Q is cross-sectional area of the stream multiplied by the speed of the water in the vertical direction, which give us equation Q equal V pi r square. Q is the same at all y and is equal to its initial value Q. So we have Q equal V0 pi r0 square. Now equalizing these two parts, we have expression for radius r as a function of v, and plugging v from question A, we have that radius r is such function of y. That was solution for question B. Solution for question C. Conservation of energy approach from part B needs to be modified to account for the work done against pressure. As we look further down in the stream, the radius is smaller. This means the pressure is higher there, and the water is slowed compared to when we assumed only gravity acted on the water. The result of accounting for changes in pressure in flow where no energy is dissipated is the Bernoulli equation. Here P0 is the pressure in the stream at the spout. Using the Young-Laplace equation to replace P and P0, delta P equals sigma multiplied by 1 over small r plus 1 over big R, we have this one. If we substantiate y0 and v as in previous parts, this equation becomes this one. This last one could be simplified to this one, which is an indirect equation to connect r as a function of y, which we don't need to solve. That was solution for question C. Solution for question D. If the size of the perturbation increases with the time, water must be flowing from the thin parts of the stream to the thick parts. For that to happen, the pressure needs to be higher in the thin parts of the stream than in the thick parts of the stream, so that the pressure gradient will force water towards the thick parts, eventually breaking the stream into droplets. We consider a small patch with a side length h on the surface of the stream at the thinnest part of the stream. The pressure is delta P thin equal this expression, and at the thickest part this expression. We are looking for the water numbers such delta P thin greater than delta P thick. To simplify this further, we will need to find small r and big R in terms of A and K, the variables given in the problem statement. A small r is the thickness of the stream, which from the equation given varies sinusoidally. R thin equal R0 minus A and R thick equal R0 plus A. We are going to need 1 over R to use the Young-Laplace equation. 1 over R thin approximately equal this one, and 1 over R thick equal this one. The inequality now like this. Next, we need to determine the radius of a curvature big R of the sinusoidal function and circle at the small deviations from the thickest part of the stream. Recall that for small theta, cosine theta approximately equal to 1 minus 1/2 theta square, which means that y sinusoidal equal a cosine kx, which is approximately this. Next, we consider a circle of radius big R. If a particle moves along such a circle at speed v, v square over r. This means that if the particle moves forward for a short time t, moves forward at distance vt and falls at distance 1/2 v square over r multiplied by t square. If we set vt equal x, then the y position of the particle y circle approximately equal y0 minus 1/2 x square over big R. Comparing, they give the same a k square equal 1 over big R. We have 1 over R thing equal negative a k x square and 1 over R thick equal a k square. Putting this into the inequality, and this simplifies to k less than 1 over r small. So the perturbations will grow as long as they have a wave number greater than 1 over the radius, or equivalently when the wavelength of the perturbation is longer than the circumference of the stream. This result was discovered experimentally by Plateau and derived theoretically by Rayleigh. The breaking up of a stream into droplets is called Plateau-Rayleigh instability. US Physics Olympiad, year 2020, USAPHO. Final round. Problem B2. Mirror, mirror on the wall. Consider a square room with a side length L. The bottom wall of the room is a perfect mirror. Remember that the phase of light reflected by a mirror changes by 180 degrees. A perfect monochromatic point source with the wavelength lambda is placed a distance d above the center of the mirror, where lambda much less than d, much less than L. Question A. On the right wall, an interference pattern emerges. What is the distance y between the bottom corner and the closest bright fringe above it? Hint: you may assume lambda much less y, much less L as well. Question B. You plan on running an experiment to determine lambda in a room with the L equal 40 meters, and you know that lambda is between 550 and 750 nanometers. You will measure d and y10, the distance of the 10th fringe from the corner, with the same ruler, with the markings of 1 millimeters. At what d should you place the point source to minimize your error in your lambda measurement? Roughly, what is that minimum error? Question C. Now suppose we place a transparent hemispherical shell of thickness S and the index of refraction n over the source such that all light from the source that directly strikes the right wall passes through the shell, and all light from the source that strikes the mirror first does not pass through the shell. At what y is the fringe closest to the bottommost corner now? You may find it convenient to use x, the largest integer below x. What is the spacing between the fringes now? Ignore any reflections or diffraction from the hemispherical shell. Question D. Now suppose the hemispherical shell is removed and we instead observe the interference pattern on the top wall. To the nearest integer, what is the total number of fringes that appear on the top wall? You may assume that d much less than L. Solution for problem B2. Question A. This setup is essentially a double slit experiment, with the second slit being the image of the point source on the other side of the mirror, with the additional phase shift from the mirror. The distance between the source and the spot, y, on the wall is given by this square root. And the distance between the image and spot y is given by this expression. Subtracting the two distances and adding in the phase shift gives us approximately this expression, which can be simplified to left side of this expression. The distance must be a multiple of lambda for interface to occur. Then this left side must be equal n lambda, where n is integer. Substantiating n equal 1 give us y equal lambda L over 8d, which is the answer for question A. Solution for question B. From a previous question we can write that 4 dy over L plus lambda over 2 equal n lambda. In our case n equal 10, it means that d multiplied by y10 equal 19 over 8 lambda L. For lambda equal 650 nanometers and L equal 40 meters, we have this expression, and to minimize our error we need to equalize d and y10, which will give us approximately 8 millimeters for both. Now, using formula for relative error, we have this expression, and if we assume that our ruler has delta d and delta y10 equal half millimeters, we have delta lambda over lambda equal 0.09, and assume that lambda equal 650 nanometers, we have delta lambda approximately equal 60 nanometers, and distance d must be around 8 millimeters. It was a solution for question B. Solution for question C. Now the optical distance between the source and the spot y on the wall is increased by n-1 multiplied by s. Then we need this equation. To minimize y, we make m to be this one, then y equal this expression. And because n-1s is just an offset, the spacing between the fringes does not change. It means that spacing is still lambda L over 4d. That was solution for question C. Solution for question D. Now the distance between the source and the spot X on the wall is given by the square root, and the distance between the image and the spot on the wall is this one, including phase shift lambda over 2. We do not assume that X much less than L this time. Subtracting the two distances gives us roughly this expression, or using Taylor expanding, we have roughly this expression. Now we can again use approximation, and we have this one, and from here we can count what is x. X equal this expression. For x to be physical, we require that m minus 1/2 less or equal to 2d over lambda. Maximum x is allowed to be L over 2, so we have this inequality. From here we can find that we have this inequality, and finally we have two conditions. From one hand, m must be greater than this expression, but less than this expression. Finally, we've got a number of fringes equal this one, and the factor 2 comes from there being two sides to the interference pattern. So that was a solution for question D, and here we made all questions solved for problem B2. US Physics Olympiad, year 2020, USAPHO, final round. Problem B3. Real expansion. Consider a real monatomic gas consisting of n atoms of a negligible volume and mass m in equilibrium inside a closed cubical container of volume V. In this real gas, the attractive forces between atoms is small but not negligible. Because these atoms have negligible volume, you can assume that the atoms do not collide with each other for the entirety of the problem. Question A. Consider an atom in the interior of this container of volume V. Suppose that the potential energy of the interaction is given by 0 when R less than D and negative epsilon multiplied by D over R power 6 when R greater or equal D, where D much less than V power 1/3 is the minimum allowed distance between two atoms. Assume the gas is uniformly distributed with the container. What is the average potential energy of this atom? Write your answer in terms of A prime equal 2 pi d cube epsilon over 3 n and V. Question B. What is the average potential energy of an atom near the boundary of the box? Assume that there is no interaction between atoms near the boundary and the box itself. Question C. Using Bernoulli's law, P plus U plus rho V square over 2 equal constant with the pressure P, potential energy density U, mass density rho and the fluid velocity V. What is the pressure at the boundary of the box? Assume the interior pressure is given by the ideal gas law. Question D. Assuming most atoms are in the interior of the box, what is the total energy of the atoms in the box? Now consider an insulated partitioned container with the two sections, each of volume V. We fill one side of the container with the n atoms of this real gas at temperature T, which the other side being vacuum. We then quickly remove the partition and let the gas expand to fill the entirety of the partitioned container. During this expansion, the energy of the gas remains unchanged. Question E. What is the final temperature of the gas after the expansion? Question F. What is the increase in the entropy of the universe as a result of this free expansion? Give your answer to first order in A prime n over V kb T. Solution for problem B3. Question A. The density of the gas is given by n over V. In a spherical shell of radius r and the thickness delta r, there are number of atoms 4 pi r square delta r multiplied by n over V. The potential energy is given by this expression. Then the potential energy is given by integral from d to infinity, which is this one. And after integration we have this expression, which is in terms of A prime n and V equal negative 2A prime n over V. That was solution for question A. Solution for question B. Now only half of the shell of radius r is full of gas and the other half is outside of the box. This means that the potential energy is lessened by a factor of 2. So we have answer negative A prime N over V. So that was a solution for question B. Solution for question C. The potential energy difference for the one atom was negative A prime multiplied by N over V. It means that the potential energy density difference is this one, which is negative A prime multiplied by N square over V square. Since there is no velocity difference, this is also the pressure difference. And due to universal gas law, we have PV equal NKT, where N is concentration of molecules, K is Boltzmann constant, and the T is absolute temperature. So it means that N equal N over V, and we have pressure inside the box is NKT over V. Then pressure on the box is this expression, pressure inside the box. So that was a solution for question C. Solution for question D. The total kinetic energy all molecules inside the box is 3 over 2 NKT. The total potential energy is potential energy for one atom multiplied by number of atoms, and we drop the factor 2 to avoid double counting. So we have potential energy equal negative A prime N square over V, and the total energy is this expression. That was a solution for question D. Solution for question E. In previous question we counted that total energy is this expression, and because energy is conserved, we have this equation to find what is final temperature. Here on the left we have volume is V, and on the right we have volume 2V. And from here we have new temperature T prime equal T minus A prime N over 3 kV. That was a solution for question E. Solution for question F. The entropy of the surroundings do not increase as a result of the free expansion. No heat is dumped to the surroundings, and the surroundings remain in thermal equilibrium. However, the entropy of the gas does increase because the gas is momentarily not in equilibrium. Therefore, we just have to compute the increase in entropy of the gas. Because entropy is a state function, we compute this change in entropy by constructing a reversible process between the initial and the final states of the expansion, and computing the change in entropy for this process. Consider constant energy reversible expansion of this gas. For this process, the work done by the gas is equal to the heat the gas takes in. Therefore, change of entropy ds equal dq over t, or equal p dv over t, where we use lowercase letters to denote the quantities during the reversible expansion. Recall that from previous we have this expression. If energy of system is E, we have this expression which is simplified to this. And from here we can express P and T as a function of V. Now we can do integration. So by definition, change of entropy delta S equal integral from V to 2V from this expression, and after substantiation P and T we got this one, and after Taylor expanding we got this expression, and this expression we can do full integral, which is this one, and energy approximately equal to 3 over 2 NKT. Finally we got change of entropy is this expression, which is answer for question F. We made all problem B3.